Okay. Right, so this is chapter 2. So, okay, before we start, maybe just to review some of the important concepts in these chapters, so which is the random variables. Okay, first of all, let's look at the more general case over here. Okay, so just some revisions. Okay, number one, so we look at definitions, 2.1.1. Okay, so this is so for this, we look at a more general case. Supposing we have one sample space with one sigma field, so a measurable space here. And supposing we have a function phi from omega to omega 1. Okay, of course, we consider this sample space that is another sigma field here. Okay, so it's a mapping over here. So we said that this phi is measurable, provided it fulfills these conditions. So it will be a reverse process. So maybe I just put it the other way around. I hope you will agree with this approach, right? So that is when B is an event in, okay, yeah, just put it like that. So that is when B is an event in F2, okay, F2 or omega 2. Okay, so whenever B is an event in F2, so then the pullback or the inverse image P inverse B is an event in F1, F. So it's from F2 and go back to F by using the reverse process for it. So this is a more general case. So in particular, when we take this to be R and this will be our Borel sigma field, then it turns out to be the so-called the random variable. So then we come to here. So that is number 2. Then we can say this. When we take omega 2 to be R, and if we take the sigma field F2 to be the Borel sigma field, then we say that it becomes a random variable. So from here, then we can see that a random variable is a measurable real value function. So in other words, we can just simply say this. Random variable is a real value measurable function. So this is the general idea for it. So however, we do have a much more easiest way to verify whether a given function is random variables or not. So which is we're going to use this theorem that is more useful for it. Okay? So I'm going to combine all this together. Okay, number 3. So I'm combining theorem 2.2.2 together with this remark. Okay. Okay, supposing we have a function x is from a a sample space omega with sigma field F to R with Borel sigma field. From here to here. So if we have that, we can see X is a random variable provided one of these following provided. So we don't have to all of them. So we just need either one of these 4 poles. Okay, so one of them. So these 4 conditions. So we can either, the first one will be 2.1. So that is X less or equals to B. So this is an event. Okay, for any number B. Alternately, maybe I shall put this one to be S2, just put a label for it. So instead of X less or equals to B, so we can take this, the preimage, X strictly less than B. Okay, either one of it. So we can either take 2.1 or S2, or we can also take this. X is greater or equals to A. So the preimage for this interval is an event for all A here. Or we can take this. So X is strictly larger than A. So we can take either one of them. So you can either stick for the first one or the second one, and third one or the fourth one. So depends on the function that we wish to consider there. Okay, so this is the most important result or the theorem in this chapter. So it provides a very simple criterion for us to check whether a given function is a random variable. So that's why in here, in a way, we may replace by it. So in a way, so you may just sort of like, so this is not that important anymore. So maybe you can just forget about it. Okay, this is, I would say that will be a working condition. So this is a general concept for it. Okay, you can just follow that. Okay, so here's an example. So we have a discrete, and this is some example of discrete random variable. Okay, so come to this. So this is for our general case. Okay, so next we have where is it? Okay, so this theorem. So this theorem 2.2.3 provide us a criterion for discrete random variable. Okay, so maybe just stay here. So number 3 or 4. So this is another important result. So we can use all this to test whether a function is a random variable. Okay, for the first one, this theorem 2.2.2. So this is actually applicable to all the cases. Okay, so in particular, if we know a given function takes only discrete value or integer value, so we can use a much more easier way to test it. Okay, supposing we have a x is a function from a sample space with a given sigma field to R equipped with the Borel sigma field, and we supposing x takes discrete value only. Okay, we know this. Okay, so when we know it discrete value, then we have a much more easiest way to check whether this is a random variable or not. So then we can see x is a random variable provided this is true. x equals to k is an event, okay, for all images k of x. Okay, that's the same. So we have gone through several examples here for the discrete case. Okay. So this is one example of the non-discrete case. Okay, so again, let's come back to here. So in fact, we do have a lots of what do you call it? Function that are random variable. Okay, so okay. Okay, so and next one, maybe some important things for it before. Okay, so just some important. Okay, number 5. So first of all, we know continuous. Function. Okay, so including increasing functions or decreasing functions. Okay, as well as this, if you have also maybe not to put it this way. So we have many of them. So maybe one by one. A, so continuous function. Okay, so we also have a increasing or decreasing function. Okay. And also you can have any this kind of the combination. So sum of two okay, all these are random variable. So you can say sum of random variables. Okay, or you can subtract, and also you can see a product of random variables. Okay, so or you can see a quotient of random variables, and all these are random variables. So or this is interesting. So we just here you look at the maximum of several random variables as well as minimums of several random variables. Okay, so all this, and we know are random variables. Okay, so which means actually most of the function that you can tell, you can name, most of them are random variables. Okay, only those are very odd kind, very funny kind of function that is not random variable. Okay, under our standard scheme for our sample space. Okay, okay, so we have briefly discussed the proof for this. Okay, so next we look at another two, actually 1, 2, 3, 3 of them. Okay, 3 important random variable. Okay, so I think this is where we stop here. Okay, let's carry on here our lecture. Okay, so this is okay, so especially so the interesting one will be this, the maximums, okay, as well as minimums of, if we consider several random variable, so we consider the maximum value of them, so that will be a random variable. So we also consider the minimum value among all these random variables, which is also a random variables. Okay. Okay, next we look at this, the positive part and the negative part for given random variables. Okay, according to the definitions, the positive part. So we have two of them, the positive part and the negative part for it. Okay, this is actually a bit misleading. The negative part, it's in fact is positive value. Okay, so just look at the definition will be given like that. So mathematically, so that will be, so the positive part of x, we just denote by x plus will be x multiply this indicator function corresponding to the set whereby x greater than 0. So that is, if you express it, that will be like this. So it will be 0 whenever x less than 0, and which is equal to x whenever x greater or equal to 0. Likewise, the negative part for x, we denoted by x minus, so it will be this negative of x when x is less than or equal to 0, and 0 when x is greater or equals to 0. Okay, so maybe the idea for positive and negative parts for given function is not so clear by looking at these two mathematical definitions. Yeah. So, however, if we demonstrate the picture, that you should get the idea or how these two functions looks like. So, for example, if we look at this. Okay, supposing we have a given function. So let's start off here. Okay, so let's say this is our function. Let's say we have a graph, picture like that. Okay. So let's say our graph of this function will be looks like this. So let's say our function looks like this. So this is our x. The original function looks like this. So if we want to look at the positive part, so that means look at here. Okay, whenever x greater or equal to 0, we take x. Whenever x less than 0, we return value 0. So that means for these two parts, we give it 0. So the graph will be looks like this. So this is x plus. Okay, so this is exactly the same. So whenever above the x-axis, so that will be exactly the same. So we got things like that. So go down here. Okay. So for this, then we fill up with 0. Okay. Similar. This is below the x-axis, so we put it as 0. But up to here, when this goes up, so then it turns out to be like this. So this is the positive part for our function. So that means we only taking the portion that is above the x-axis. So those portions below the x-axis, we level it to the x-axis here. Now, if we look at it, so then we can get the negative part. So that will be like this. So the negative part will be the other way around. So for those on top, above the x-axis, so we put it here, level to the x-axis. So it turns out to be like this. Up to here, and this will be 0. Okay. So whereas for the portion that is below the x-axis, we sort of like we reflected it like this up to here. So So if we do the refractions, then it becomes like that. So this part we do a refraction, so it becomes like that. And similarly, so this one we do a refraction. To here and go down. Okay, so this is one. So this is why I'm saying that it's a bit misleading, although we call it the negative part. If you look at the graph here, so this function is actually always greater or equal to 0. Okay, so that these functions always non-negative. And this is always non-negative. So whereas this has positive and negative part. Okay, so this is the positive part and negative part. So I think the next is straightforward, this remark. So we have this formula, x must be equals to x plus minus x minus. So you can see when you put a minus, right? So you actually go down, go back to it. So I don't think I need to propertify. So let's say we change the color here instead of the green color. Okay. So this is the x, right? So if you look at minus of x, so this will be level, no change, level, right? Minus of 0 will be 0. So however, the positive one, it will go down here. And this one will go down. And you will things like that. Okay, so if you're combining this green color portion and this, then it turns out go back to our x. So that's why from this graph, then you can see these conclusions. So x always equals to x plus minus x minus, or you can put it this way: x plus will be x plus minus of x minus. Okay. So next, I think you guys, I believe you guys know the meaning of module of x. Module of x will be, we just look at the magnitude, sorry. So that's why you can see module of x will be x plus x minus. So you just need to remember, then we have this. So modulus of x is equals to x plus x minus. Okay, or I think we better put this one. So we have two these mathematical relations between this modulus of x with x plus and x minus here. So alternately, then we can say x plus will be the maximum of x and 0. X minus will be the maximum of negative x and 0. So I just look at here, I think you get a picture. So you consider maximum of x and 0. So when you look at this part, x will be always less than 0. So that's why we take 0, right? When we come to these portions, so this part always larger than 0. So that's why we take this. So come to here, we have the same argument. This portion is less than 0. So that's why we take 0 and here. So x plus will be given by this. X minus will be given by this. Okay, now we just go back to this. Okay, maybe here. And we have this. It's clear. X plus will be, because we are only two of them, so we can say this is maximum of x and 0. Okay, and x minus is maximum of minus x and 0. Okay, next we go back to the result here. Okay, from here, we have this theorem. So whenever x and y are random variable, okay, maximum of xy is a random variable. Okay, so we come back to this. based on our setting, so this is a random variable. Okay, so a constant function is always a random variable, right? So if we look at here, then we can see x plus is a max of this. So this one is also a random variable. So this is directly by our theorems here. So this one. Okay, so this is by theorem. Okay, likewise, x is a random variable, so that means we look at here, we're taking a to be -1, b to be 0, so minus of x must be a random variable. So we know this is also a random variable, and 0 is a random variable. So I think you agree with this, right? So then we can see this is also a random variable. So by theorem 2.3.1. So this one is also a random variable. So then now we know x plus is a random variable, x minus is a random variable. Yeah, based on this, maybe be more specific, we look at part B for this theorems. Yeah. Next, we look at here, modulus of x is x plus plus x minus. So here we know x plus is a random variable, x minus is a random variable, and here the sum of two random variables is a random variable. Then from here we can also conclude that this is also a random variable. So we by using theorem 2.3.1, but we are using part A. Okay. So from this argument, then we can see x is a random variable, then x plus x minus and modulus x are also random variable. So the argument we directly from theorem 2.3.1 A and C. Why is part C? Oh, okay, doesn't matter. So this is okay. So let's come back to here. So we can see actually a lots of function that we can tell are random variable. So which including x plus and x minus and modulus of x as well. Okay, next we come to, this is actually the second topics for our chapter 2 here. Okay, so this is the first part. So we are talking about random variable and some of the properties of the random variable. Okay, so the second part will be here, the probability distribution of a random variable. Okay. Maybe up to here. So then this is we discuss the concept of. This is we discuss the concept of random variable and some of the mathematical behavior or properties. Okay, and some examples of it. Okay, forget about the example. Okay, so this is the first topic. So we discuss this random variables. Okay, next. This is part A in chapter 2. Okay, next we come to this probability distributions of a random variable. Okay, so part B, then we discuss how is it? You see how to we construct how should I say? It's like a new probability. on R. So using a random variable. So this is a topic that we're going to discuss. Okay, so we discuss how to construct a new probability on R and using a new random variable. Okay, in fact, the probability that we constructed here. So this is actually you have already seen this thing in your undergraduate statistics course. So this thing is actually what we so-called the distributions. Right? So which including all these we so-called binomial distributions, normal distribution, beta distribution, GF distribution, and blah blah blah. So all those distributions are actually belongs to here. Yeah, that is at first we have a given sample space, okay, and a given sigma field, and then we consider some kind of the random variable on that sample space, and then we use that random variable to construct new probability, and all those will be distribution. Okay, in a way you can say a distributions is a probability which related to a random variable. So you can put in that way. Okay, so let's look at the construction first. Okay, before that, so we have to ensure the construction is a random, is a probability on R. Yeah. Okay, so the setting will be like that. First of all, let's say we have this. Let's say we have a sample space. Okay. Okay, so the setting like that. So given. So we have a X. We have not X. We have omega. Okay, then we have a F. Okay. So then this is already here. R, we know real numbers are already always there, and its sigma field always there. Okay. So now let's say we have a random variable. We define a random variable is a function defined from R. So this is a random variable. And according to our setting, okay, so let's go back to here. What is a measurable function? So a measurable function is a function which pull back event from here and back to an event in here. Okay? So that means by using the inverse function. So from here, then based on here, then we can this we have a B, R, and this one F. So the inverse of it, so it go back to it. Okay, we take any events here and come to another events over here. Okay, but the different environment is sort of like this is in one country. Okay, event is somebody in this country. Let's say in you can put it in UK. So this is Malaysia. Okay. So okay, so this is sort of like it brings one citizen in UK and go to another citizen in Malaysia. Okay, by using this process here. Okay. So event to event here. Okay, now and supposing we have a sample space with sigma field, and let's say we already know we have a probability measure over here. So this is a probability space. Okay. So here we do not have a probability over here. Okay. So how we're going to define it? So we're going to use this process to construct this probability. Okay. So this one go back here, and probability measure we know which is defined on here. So then we have a P to R. Okay, or to be more precise, then this is a P2, this the closed interval 0 to 1. Okay, now we can see we're using this process. We come to here, we go down here, then we actually have a relations to link all the event to another event, to one probability over here. Okay, so it's a P of the event, right? Then we come to here, then using these two processes we combine, then we can define this a new case. So that is from here we come to here, back to 0, 1. Okay, so this is S2. So we just simply call the combination of these two processes as PX. Okay, so if we put it in terms of functions, so mathematically, so Px will be just P composite with the inverse form X. Mathematically, we can express in this way. Okay, forget about it. Okay. So using this way, then we have construct this function. So we have constructed a function. Okay, so that is we just simply put Px of anything here to be P of the inverse of this. Okay, whereas we always take this to be event, maybe a Borel set. Okay, so we have constructed this. So then before that, we need to verify this Px is a probability measure. So under this construction, then we have here this theorem. Okay, so then we can see this Px is a probability measure on R. So again, what is meant by a probability measure? So then we have to go back to something. Okay, so this is go back to the definition from probability measure. Okay, so a given function p from f to this is a probability measure if and only it satisfies these three conditions. Okay, so that means we come back to this. We want to ensure this px will fulfill this 1, 2, 3 actions. Okay, so this is what we want to. Of course, in here we are taking f to be BR. Okay, so instead of F, so we're actually taking this to be our BR here. Okay, so let's look at the proof for it. Okay, so we want to verify these three of it. And also, this P, the given P is a probability measure, so it's always fulfill these three conditions here. Okay, so we do it one by one. Okay, let's do the first one. Okay, so Px of, okay, because now we are doing this thing on R, right? So that's why now we are taking this to be our new omega. Yeah, so which is R. So P of R, okay, according to the definition, it's P of X inverse R. Okay. So R is a whole thing. So then you reverse back, that will be P of omega. So, and this is must be equals to 1. Okay, so this is equals to 1. So the reason is because we know P is a probability measure. Okay, maybe I will say P is a probability on omega. Okay, so this must be what it always will be. So that's why we get the first criteria pass. So we go to the second one. Next, for a Borel set B. So Borel set here means the event in R. So we can see Bx of B. So it's the same definitions here. So that is P of X inverse of B. And according to, again, P is a probability on here. So P of any event must be larger than 0. So this one must be greater or equal to 0. Again, the same reason. So this is just simply because of P is a probability on omega. Okay. And X inverse of B is an event on F. And lastly, we need to verify 3. Okay, so supposing we have a A1, A2 which are disjoint, okay, in event, then we want to show this relation holds. So what we can do is we let, let's say, A1, A2, and so on are disjoint Borel set. Okay, so first of all, this is very important. We only consider disjoint one. Okay, so we want to show this relations always holds. So then we can just use to do the calculations. So then Px of union of all the AK. Again, according to the definition, so that is P of X inverse of all the AK. Okay, so again, we want to show this is actually written in this way, right? Okay, next we go back to properties over here. So according to here, so we look at A. So whenever inverse of A or B, we can put it in this way. So that means we can apply into here. We can actually sort of like take out this union here. So then this is equals to P of union of all the X inverse AK. Okay. So we have this. So this is actually by remark 2.1.1a. Okay, we're using this value. Okay, now because of all these are disjoint, and we can see these are disjoint. Then we also have note that this is also disjoint. Also disjoint. event in omega. Okay. So that is straightforward because of when this is destroyed, so the pre-image or the inverse image must be destroyed. So when this is destroyed, then we can apply this property to our P here. Okay. So then we can see P can become like that. Some may think all the K from 1 to infinity, P of X inverse of AK. Okay, so we make use of this property. And next we use back to our definition. So this get back to summating P of X of AK. Okay, so we can see our PX fulfill this property 3. This is true for all destroyed event AK. Okay, so when 1, 2, 3 all true for this PX, then we can make a conclusion. Hence, so this PX is a probability measure on R. So this is how we get this. Oh, actually, the proof is actually already here. So okay, so just write it one more time, sort of like just need to change the symbol from B to A. Okay, the rest are the same. Okay, now we have verified. Okay, like I said, let's look at our setting here. So actually, first of all, we begin with this probability space omega F and P. Then we use a random variable X to relate this omega to R. And because of this is a random variable, we can use the inverse of this random variable to relate every Borel sigma field, Borel set in here go to an event in F here. Yeah, so we have a relationship between a Borel set in R and events in this original sample space. Okay, and according to our setting, this sample space or this sigma field always equipped with one probability space P. So this one already know. Okay, so we can use this X inverse combined with this P to construct a new PX. Okay, okay, now everything done. So first we can sort of like we use X to relate to this. Okay, we have a relationship. Okay, maybe then this F we're going to relate to this by using the pre-inverse. Okay, then we can use this P to construct another probability to it. So something new. So that is a PX. Yeah. So as we have already verified just now, this PX is a probability measure on R. Then using this omega F and P, we can construct a PX on R and BR. Okay. Right. So this is we have discussed in theorem 2.4. Okay. Once we have verified that this PX is a probability measure, that can have a new probability space over here. R, B, and this PX. Okay. So we have a special title for it. Okay, so in this case, so this PX that we have constructed, we just simply call it distributions of X. Okay, so from here you can see here because this P always related or associated with a random variable. Okay, it cannot be independent from anything. You have to rely on one random variable to construct. Okay, so that's why we can say these are distributions of x. So px will be defined like it. Okay, next we can use this to define a new thing so-called the distribution function. Okay, maybe up. Okay, why we want to have a distribution function? Okay, maybe later on I'm going to discuss it. Okay, so that's the end of proof. Okay. Next, we have something so-called df, the distribution function, which is a capital X. This, I believe you know this. You have seen this before. Next, we say two random variable x and y are identically distributed if fx equals to fy. So we just use this. Okay, we forget about part 3 first. We look at the part 1, part 2, part A and part B. So if you look at here, px is actually on top of it. So we can see first omega and r. Okay, x is a function from omega to r, right? So then the px is actually the functions from br to 0 to 1. Okay, so no issue. It's just that we are relate any event here or a product set to a probability here. Maybe a value. Okay. So the thing is, this is a set. So when we want to relate a set to, let's say, things will be a little bit complicated, right? So this one a little bit. Complicated because we involve a set here. So because so then to make things easy, so we define this into here. So fx is actually defined on a number here, value. So then we can construct this. So t is a number, so that means now we can see this distribution function fx so it defined on r. Okay, so that's why in here, in a way, so this one is not that complicated. So this is a simpler because of domain. Subset. Maybe we basically because of it's defines on numbers only. Okay, instead of set. So that's why it will be easier. Sometimes we use distribution functions to start to analyze the things. Okay, so next we have a concept of equality of random variable, so which is slightly different from the usual sense. Okay, we said this x equals to y if only p equals to x proper 1. So not x omega equals to y omega in here. Okay, so the idea is like it. When we consider two random variables, we said they are identical. We do not need to require them to be exactly the same. So we allow them to have a small discrepancy. So as long as it's produce the same probability, then we said they are the same. So for example, we can see, just look at example. So let's say if you look at the x is like defined like this. So the graph is like this. So let's say you look at these functions. Okay, so it's like that. So, but not here. Okay, then it dropped to here. Okay, and then it's 3, then 0 here. Okay, so this is our function x. Okay, so it 1 and then 0, 0 here. Okay, next we look at this. So you look at y is another function. Okay, now instead of there are two holes here, so y is a function, we only take values 1. So I think if you look at these two pictures, clearly x and y are not the same because of for x there are two holes here. Okay, but the remaining are same. Okay, if you look at here, these two holes will not affect the probability if we were said right. So that's why we can see x identical to y. Okay, although x not equals to y. If you look at the graph, okay. So that's the ideal rate. So because we're only concerned with the probabilities for the random induced by the random variable. So even these two random variables not exactly the same. The sum of value might be varied. However, if they produce the same probability or the same distributions, we say they are identical. Okay. So we said two random variables are identical in this sense. Okay? So which is slightly different from the usual concept, okay? Which is a weaker requirement to it. And anyway, we will come back to this later, a little bit more detail in chapter 5. Okay, so just a rough idea. Okay, understand the rough ideas over here first. Okay, okay, next. So this is a very important idea. Things we have 3 important properties for our distributions functions. Okay, so this capital fx. Okay, first, fx is an increasing functions. Secondly, when t go to negative infinity, it will be 0. When t to positive 1. So this is a right continuous. Okay, so that means when you come from the right, so you can get the value. So can give you the idea for the graph. So okay, maybe I will use a graph easier. Okay, so it will be easier. So again, this is a function from R to R. So let's say this is the domain. T. Okay, T or X. Okay, so let's say this is Y. Okay. Okay, first of all, this is increasing, so that means the graph is always going up. Okay, going up. And when you go to negative infinity with 0, okay, maybe I just draw 2 lines first. So this is the value 1, this is the value 0. Okay, so it's always in between here. When go to negative infinity, value 0, so that means it will be when you go here, you will be close to 0. Okay. When you come to here, it will approach to 1, but it might touch or it might not touch. Okay, so stuff like that. So and which is increasing, so that means it cannot be like this. Yeah, it cannot be like this. It cannot be like this. Okay, so it's always going up. So not necessarily continuous, so it can be going up like this. Go up. Go up. Okay. Like that. And also, it's right continuous. So that means when you come from the right, you may reach the end. So the end is here. Okay, and this one, no. So there's a hole here. If there's disjoint, okay, there's the end here. So there's a hole here. There's the end here. So this is what that means when you come from the right side, you may stand here, but if you come from left, you cannot stand over here. So this is the property for, this graph can illustrate these three properties for the distribution functions, okay? First of all, increasing must be going up like that. Next, when you go to this side, you will approach the x-axis. Here will go to 1, and that is a right continuous. Yeah. Okay, so let's look at this. So one by one, first, want to show this is an increasing. Okay, so before that, just this is one. Okay, so when s less or equal to t, I think it's clear, right? This one must be a subset to this. Whenever s less or equal to t, like this. So then p of this must be less or equal to this. So because this event is smaller than this event, so the probability for this event must be less or equal to the probability of this event. And by definition, this is a fxs and this fxt. So then this is what we can have. So so theorem 2.3.1. Okay. So we can see so I'm not going to, the proof is already here. So maybe I would just say this is the sketch of proof. Okay, sketch of proof. Okay, number one. So we have shown that. Okay, we have shown that. This is the case. So according to the definitions, whenever s less or equals to t implies fxs less or equals to fxt. Okay, so whenever we have this, so then this will simply means it's increasing. So that's why we get the first one. Okay, next limit things. Okay, this one I just look at one of it. So the other one you can do it similarly. Yeah? So we look at it. Number 2. Okay, so limit t to minus infinity fx of t. Okay, so this is equals to this one, which is actually equivalent to consider this. K to infinity f of x of negative k, right? K is an integer. So according to the definitions, so this is equals to limit k to infinity p of x less or equals to k. Okay, so I think maybe this is the thing. Just take up this one. Just look at this one. Okay. Right. So I think we can. Okay. Right. First of all, one and this. First of all, -1 is larger than minus 2, right? So that's why this must include this as a subset, right? Similarly, you look at x less or equals to minus 3. Again, minus 2 is larger than minus 3, so we have to include this as a subset. So we follow this process, then we can get it. So if you look at this process, then we can see this is a decreasing sequence of set. So we just go back to our chapter 1. Chapter 1, chapter 0. So I think not chapter 1, this is the chapter. So go back to our chapter 0. Okay. Yeah, I think it's a chapter 1. Okay, so this is the case here. Okay. So let's look at this theorem. Okay, 1.4.3. So, okay, yeah, we are looking at this. Huh? Okay, if Bn is a decreasing sequence, okay, then limit of PBn will be equals to P of intersection of them. So now if you look at here, so that means now we can take in this to be B1. So let's subset our superset B2 and superset B3, right? Okay. So that means then we can see this is n, Bn is decreasing. Okay. Bn is decreasing. So now we can apply this result. So this is actually this one. So that means it will be the intersection. Okay. So hence, then we can say this is equals to okay, P of the intersection of all of them, x less or equals to minus k. K is from 1 to infinity. So how do we get this? So this actually by theorem 1.4.3b. And if you look at here, you k -1, -2, -3. So this thing will end up to be negative infinity, right? And because of x only take real number, so that's why this will be empty set. P of the empty set, that will be 0. So for the second limits, you can get it in a similar way, but the only difference is in the second limit, you're going to use I think it's an increasing one. Okay, so I leave it to you. You do the exercise. Okay, you do it on yourself. So just an exercise for you. Okay, so for part 3, what is part 3? Okay, fx is right continuous. So that means limit epsilon to 0 positive fxt plus epsilon is fxt. Okay, in fact, this can be proven by using the similar ideas here. Okay, so maybe since we have started this, right? So let's look at this, number 3. So this is what we want, limit epsilon to 0 positive fx of t plus epsilon. So the proof is similar. So what we can do is we can get, this is actually limit so epsilon go to 0 from the right. Okay, so that means it getting 0 smaller as well. So we can say this is a k to infinity fx t plus 1 over k. Right, so when k to infinity, 1 over k will approaches to 0. So that's why we can put it in this way. So next, we put in the definitions for f. That will be limit k to infinity. So this part will be the probability of x less than or equal t plus 1 over k. So again, same idea. Then you can see this x less or equals to t plus 1 over k. So this one, all these are decreasing. You can verify it similar to the case 2 are decreasing. Okay, so when this is decreasing, so we can refer back to the same formula once again. So we're going to use this formula once again. When we have a decreasing sequence of events, so we can have a formula like this. Yeah? So then we use the same form theorems. Then we can see this is equals to P of the intersection of this event x less or equals to t plus 1 over k. Again, k running from 1 to infinity. So so we have discussed a similar thing in chapter 1 and chapter 0 already. So this one you guys can check, this is less than t. So by the definitions, so this is equals to fx t. So again, you can see it's not difficult. We just need to apply theorem 1.3.4. Okay, I hope by going through the proof for this, you have some idea how to apply this kind of formula to solve our problems here. Okay, so the next one, we are not going to look at the proof for it, but just give you the ideas for it. Okay? Any real value function f satisfied the three property above is a distribution of a random variable x. Yeah. So that is the idea for it. First of all, let's say if we have an x from our previous setting. So this x is a random variable. Yeah, it's a random variable. So if we have a random variable, then we can use this x to construct a px, and then we can use it to construct a fx, right? So this is something so-called a distribution function. Okay, so it's always fulfill these three. 1, 2, 3 in theorem 2.4.3. This is 4. Okay. So if you have a random variable, we can always use this random variable to generate a distribution function. That is something which always fulfill the property 1 to 3 in theorem 2.4.3. So this 1, 2, 3. Okay, it's always fulfill these three actions. We call it. Now, the reverse process is also true. Okay, so that is supposing we have given an x f. Okay, so we don't know that. So we only know this f fulfill properties 1 to 3 in theorems 2.3.4. Okay, so in fact we can use it to construct an x, and it can be verified this x must be a random variable. Yeah, it's sort of like if we have an x, we can use an x to construct something so-called distribution functions, which fulfill the 3 properties. So the other way around, if we have a function which fulfill the 3 action in theorem 2.4.3, we can use this f to construct a random variable. So that means these two have a relationship between these two concepts. A random variable is always related nicely to something so-called distribution function. Okay. So however, just to let you know this idea, we are not going to go through the proof for this thing. So since we can always construct a random variable by using something so-called distribution functions. Okay. So we are not looking at proof for it. Okay. So this leave it. Okay. So let's look at some examples here. Okay. Okay. First of all, we look at it. Okay, I'm not going to look at how we're going to construct this random variable. However, we can just look at this example here. Then we can see we use it to construct the random variable. Okay, let's say we look at this function. Ft is we integrate this e negative t this. Then you guys can work out the calculation. So f satisfies the 3 properties 1 to 3 in theorem 2.4.3. Okay, so if you consider f of t is equals to this. Yes. So of course, since we didn't mention the property, so that maybe always take this as what do you call it? Okay, so this is okay. Sorry, I think so. This one. Okay, so I think from here, then you can check carefully, easily. So first of all, it's always fulfill the 3 properties. So this is an integration, and this is a positive. So then you can see the graph. Maybe you can look at the graph for it. The graph is always like this. No, sorry. This is a graph, and this is a positive functions, right? So this is sort of like and this is always a positive. So this one, in a way, you can say this is in a way, this is an area under the domain. Okay, so area under the domain. So when you increase, so that's why it's always increasing. So that's why if you look at it, so this is provided this is always positive. Okay, so the graph is always positive, then this is always increasing. And also, secondly, then you can check easily. So when they go to negative, you get 0. When go to infinity, you get 1. Okay, so I think the 2 is also quite clear. And number 3, this is a continuous function, so that's why this is always true. So this is the one. Okay, then you can easily see if satisfies 3 properties, then this is a distribution function. So you can define a probability measure. So this is the one. And this is so-called the, you can see this is an exponential distributions, right? So you define it, then you can define your, what do you call it, the random variable on it. So the next examples, this is X defined on this probability space, omega, F, and P. So X omega equals to 0 for all omega in the sample space. Okay. So then P of X equals 0 is always equals to 1. Right, because you only take one value, right? So this is actually we so-called a discrete. So this is actually a discrete one. Okay, forget it. Okay, so this is a discrete one. So in fact, only one value. Yeah. So that's why X omega 0. So P of X equals to 0 is equals to 1. So Px will be this. So this one you get it. So that means you can see clearly. So the graph looks like this. So this is the x-axis, this is the y-axis, this is the value, 1. So this is actually sort of like the Bernoulli. Okay, so the next one. So omega is a head of tail, so we define xh to be 1, xt to be 0. So P, if P assign equal probability on H and T, so that means Px equals 0 is half, Px equals 1 is also half. So this is actually, this is so-called the Bernoulli distributions. Okay? So we're tossing a fair coin. So in this case, Fx will be this. Okay? So you can see the graph will be this one. So this is our y-axis. So this is our x-axis. And this is the value, half. This is the value, 1. So what I want to highlight will be, you can see this bit. So this is what we so-call the right continuous. Okay, so this is right continuous and right continuous. Okay, so this is actually, I think we can discuss it first. Later on, we can look at this thing for it. X is a random variable, so we have a PDF density functions. Small f will be given like that. Then the capital F will be this. So this is actually the idea, you should have already learned this in your probability theory. Okay, never mind. So we discuss it later. Maybe we look at it after our definition 2.5.3 here. So I think maybe we just stop here. Okay, I think we stop here, and then we take, as usual, take a break for half an hour. So we carry on our second section on 8 p.m. right? Okay, I have a question from Sakashning. How many chapters do we have in total? 6. Okay, altogether 6 chapters. Okay, let's take a break for half an hour. Okay, we come back after 8 o'clock.